Have you ever wondered how we mathematically identify hidden symmetries within a shape? Or what exact conditions allow a space to even admit a covering space in the first place? Today, we outline the answers to those questions by examining the abstract framework detailed in sections 81 and 82 of James Munkres Topology. The core philosophy of algebraic topology is converting complex geometric relationships into solvable algebraic rules. We accomplish this by mapping topological spaces to their fundamental groups and relating covering spaces directly to subgroups. Mastering this mathematical translation builds a dictionary. It allows us to determine the global structure of a topological space by simply analyzing the algebraic behavior of its fundamental group. Let's start with the concept of a covering transformation, also known as a deck transformation. Think of this as a homeomorphism from the covering space to itself. It shuffles the layers up in the fiber, but it leaves the projection down to the bake space perfectly intact. These transformations form a distinct group. When a covering space has enough of these transformations to map any point in a fiber to any other point in that same fiber, we call the space regular. Algebraically, this occurs strictly when the subgroup H0 is a normal subgroup of the fundamental group. This diagram shows the classic example of a regular cover, the real line wrapping over a circle. Because the fundamental group of a circle is abelian, every subgroup is normal. Shifting this helix vertically by whole integer steps perfectly overlaps itself, revealing its symmetry. Compare that to this diagram of a non-regular covering space for the figure 8. The x-axis wraps exclusively around circle A, while the y-axis wraps around circle B. You cannot symmetrically shift this cross-shaped structure onto itself while maintaining the projection map. The algebraic property of regularity is simply the geometric manifestation of maximum mathematical symmetry. To construct regular covers, we look at group actions. A group action is properly discontinuous if for any point we can draw a small neighborhood that, when operated on by the group elements, scatters into completely separate, non-overlapping regions across the space. Theorem 81.5 formalizes why this is useful, as shown in this commutative diagram. If you map a path-connected space down to its orbit space, defined by a properly discontinuous group action, the resulting projection map is automatically a regular covering map. Utilizing orbit spaces provides topologists with a reliable engine for generating regular covering spaces from scratch. We can classify covering spaces effectively, but given an arbitrary subgroup, how do we prove a matching covering space actually exists? The prerequisite for existence is a property called semi-local simple connectedness. Look at the text here detailing the infinite earring. Any neighborhood around the origin traps an infinite number of circles. It fails the condition, meaning it cannot possess a universal covering space. When a space meets the condition, Theorem 82.1 provides the construction method. As shown in the base space B, we can build the points of the covering space E above it using equivalence classes of paths originating from a starting point. Two paths, like alpha and beta, are equivalent if the round-trip loop formed by traveling out and coming back in reverse belongs entirely to our target subgroup. What happens to this equivalence relation if our target subgroup is completely trivial? If the subgroup is trivial, the round trip must be equivalent to staying completely still. The paths must be strictly path homotopic. That specific constraint gives us the exact recipe for constructing a universal covering space. Here is the completed topological dictionary. First, covering transformations precisely measure internal symmetries. Second, regular covers represent the peak of those symmetries, mapping to normal subgroups. Third, the actual existence of these covers relies on the space's local structure, specifically semi-local simple connectedness. Mapping these geometric concepts into algebra establishes the Galois theory of covering spaces. It operates as a perfect theoretical mirror connecting the shape of a space to the strict rules of group theory. For the full mathematical proofs, review sections 81 and 82 in Munkres Topology. And if this breakdown helped clarify the concepts, subscribe to the channel for more guided mathematics.